Hello guys, during this video series I would like to talk about the digital design and concept of designing a digital circuit. So for this reason we will start to talk about the binary systems and the also Boolean algebra and the Boolean function. Then we will talk about the different sections of this digital design course. I hope this course will help you to understand the concept of the digital design system. So before starting to talk about the uh, actually digital design course, I would like to talk about the our uh, main reference, one of the famous books in the case of the digital systems, which is called The Digital Design, written by Demarius Maunod. This book is one of the most famous books in the case of the digital design, and I will actually teach all of the topics related to the digital design during this video series from this book. So first of all, let's start to talk about the syllabus of this course. In the chapter 1, we will talk about the digital systems and binary numbers, because you know that the uh, fundamental concept of the digital systems are the binary numbers, and we know that the digital systems work with the binary systems. For this reason, we have to learn about these binary numbers and learn that how we can convert the different types of the numbers like decimal numbers, uh, octal numbers, and hexadecimal numbers to the binary numbers. In the chapter 2, we will talk about the Boolean algebra and logic gates. So we know that the actually basic elements of the digital circuits are the logic gates, and here in this chapter we will learn that what are the different types of the logic gates and how we can use them to actually implement the digital circuits. So in the chapter 3 we will start to talk about the gate level minimization. What is the meaning of the gate level minimization? You know that all of the designers, when want to design a circuit or design a system, it doesn't matter this system is a circuit or not, try to design the simplest one, because designing the simplest system will help us to work with this system better and better. We also in this course want to show you that how we can minimize these actually Boolean functions before designing these Boolean functions and implementing these Boolean functions with the logic gates. After learning the concept of the digital systems and digital circuits during these 3 chapters, we will start to talk about the combinational logic. Combinational logics are the kind of the actually digital circuits that we will see that how we can implement, how we can design these types of the system, and also how we can analyze this type of the system. In the chapter 5 we will talk about the sequential logics, and in the sequential logic we will see that sometimes the digital systems need to have memory, and how we can add the memory in the digital systems. And in this chapter we will talk about the flip-flops, and you will see that a flip-flop is is an element that can store 1 bit. In the chapter 6 we will talk about the application of the combinational and sequential logic circuits like registers and counters, and at the end in the chapter 7 we will talk about the memory, and we know that one of the 2 important memories in the digital systems are RAM and ROM, and we will learn how we can design a RAM, how we can design the ROM, and what are the structures of these memories. These 7 chapters are the syllabus of this course, and I will actually teach you all of these topics during this video series. So let's start. First of all, I want to talk about the concept of the system. So if I want to actually define a system, we can say that system is an interconnection of the elements that connected together to work something to have one purpose. This is the general definition of the system. It doesn't matter what kind of the system do we have. This definition accepted for all of the different types of the system. So generally, we can divide this system to the main category. One is the analog systems, and another type of the system can be divided to the digital systems. So what is the analog system and what is the digital system? We say that if we have a system and we know that each system has input or inputs, this input can be one or more than one, and also output. This is the system. So we say that if the input of a system is analog signal, and output of a system is also analog signal, we called this type of the system as analog system. On the other hand, if I have a system that its input is the digital signal and output is also digital signal, we called this type of the system as digital system. So the question is that what is the analog signal? What is the analog signal and what is the digital signal? We say that if the value of the signal during time changes continuously, like something like that. If we suppose that this is t, suppose that here is t1, here is t2, here is t3, and also here is y1, y2, and y3. It doesn't matter. So you can see that at each value of the time, for example, this t1 can be 0.52 seconds. This one can be 3.48, I don't know, second. So, and also y1 can be 10.021 or y2 can be 15. It doesn't matter. The important thing is that during the time, continuously when the value changes, we call this type of the signal as analog signal. So on the other hand, if I have a signal that has discrete values, something like that, at a distinct value of time for 1, 2, 3, 4, 5. So we called this type of the system as discrete signal. Okay, so one type of the discrete signals that has just two values called as digital signal. What does it mean? It means that if I have something like that, look at here, you can see that we call here is 1, 0. We can see that during the time, if this is, for example, x of t, our x of t has just two values, 1 and 0. So this type of the signal is called as digital signal. So it doesn't matter the value of this signal is 0 and 1. You can draw or have the digital signal something like that. Again, also you can see that if, for example, here is +1, here is -5, and also you can see that this is the digital signal because has just two values, +5, -5. So normally in the electrical and electronics engineering, we call this one as 5 volt, for example, 3.3 volt, for example, 12 volt, and this 0 as 0 volt. Important thing is that always we have just two values for it. Okay, now let's continue with our slides, and I explain in detail that what's happening. So I said that the digital systems are used in different actually concepts like communication, business transactions, traffic control, medical treatment, weather monitoring in the internet, and something like that. And we said that one characteristic of the digital systems is their ability to represent and manipulate the discrete element of information. So what is the discrete elements of the information? For example, 10 decimal digits are the discrete elements, 26 letters of the alphabet, and also 52 playing cards are the actually discrete elements. Now we say that these discrete elements of information are represented in a digital system by physical quantities which are called as signals. Now, when this signal has two discrete values, we call this as the binary. We call this one as binary. So it is so important, this concept in the digital system. Why? Because we have just two discrete values. Here is 0 and 1. So this binary digit called as bit, and this bit is 0 and 1. It means that each of the 0 and 1 are 1 bit. So the actually groups of these bits, are called the binary codes, that these binary codes are used in the digital system. For example, 0, 1, 1, 0, 1, 1, 0, 1, 1. This is a kind of the binary codes that has meaning. And we will use these discretes, these actually digital, as a signal, input signal, give it to the digital system and receive the other digital signal. Okay, now from the primary school we have learned that how we can represent numbers in the decimal system, and we know that in the decimal system we have something like that. If, for example, if we have 753, we have learned that we have rewrite this number or expand this number in this form, 753. On the other hand, we can rewrite this one in this form, 7 multiplying by 10 to the power of 2 plus 5 multiplying by 10 to the power of 1 plus 3 multiplying by 10 to the power of 0. So we can see that these tens represent the actually base of a number, and we called these tens as base or radix of a numbering system. And these 7, 5, and 3s are called as coefficients. And the power of 10, 0, 1, 2 represent the value place of each coefficient that you can see here. The value of the place of each coefficients. Generally, we can represent each numbers in this form: A3, A2, A1, that if we have fraction part, A minus 1, A minus 2, A minus 3, etc. So here we have to write the actually number of the base, because we will see that the different numbers can be represented in the same form, but this is the problem if we don't write the R here. So if I expand this actually general form, I can say that plus A3 multiplying by R to the power of 3. I'm so sorry, here also I have to write a 0. Here we have a 0 plus a2 multiplying by R to the power of 2 plus a1 multiplying by R to the power of 1 plus a0 multiplying by R to the power of 0 plus, now we continue the fraction part in the form of a minus 1 multiplying by 10 to the power of minus 1 plus a minus 2 multiplying by 10 to the power of minus 2 plus etc. So this is the expansion of the general form of a number. So we saw that if R here, if R is equal to 10, how many digits do we need to represent a number in the decimal? In the decimal system, we know that the numbers start from 0, 1, 2, up to 9. When R is equal to 5, how many digits do we need? 0, 1, 2, 3, and 4. If R is equal to 8, which is called as octal system, we need the 0, 1, up to 7. And if R is equal to 2, we call this type of the system as binary system, and we need just 0 and 1. Generally, you can see that in the R-based system, the digits that we need start from 0 up to R minus 1. So if we have R is equal to 16, we need from 0, 1, 2, up to 9, then 10, 11, 12, 13, 14, and 15. Because R is 16, R minus 1, 16 minus 1 number digits, we need to represent a number in the 16 base, which is called as hexadecimal system or hex. Now, you know that because the 10, 11 up to 15 represented by 2 digits, when we want to represent a number in the hexadecimal form, we cannot represent these 2 digits. Because, for example, if I write something like that, we cannot understand that this is 10 or 10. For this reason, we say that instead of 10, write A, instead of 11, B, instead of 12, C, 13, D, 14, E, and 15, F. Now, if we want to represent the 10, we have to write that A, 5, 4 in the base of the 16. So this is the general concept of actually hexadecimal, that we want to represent them in this form. And you can see that here in the case of the decimal system, we can represent these numbers in this form. And generally, I explained that we can represent the numbers in this form. In the case of the decimal numbers, we can show the numbers and expand them in this form that you can see here. So in the case of the radix actually binary system, you can see that same thing happens if we have a number and we can rewrite or expand number by its radix and base and powers as the place value of each number. For example, if I have something like that, in the case of the binary number 1, let's write it here, 1 1 0 1 1 in the base of 2. So we learned that from the right side, the base, actually the value place of this number is 2 to the power of 0. The place value of this one is 2 to the power of 1. This one is 2 to the power of 2. This one is 2 to the power of 3. And this one is 2 to the power of 4. It means that I can rewrite and expand this number in this form. 1 multiplying by 2 to the power of 4 plus 1 multiplying by 2 to the power of 3 plus 0 multiplying by 2 to the power of 2 plus 1 multiplying by 2 to the power of 1 plus 1 multiplying by 2 to the power of 0. And we will learn that if I calculate this value, I can find the value, the corresponding value of this number, which is written in the binary number. We can find the corresponding number in the decimal number. Anyway, I will talk about that in detail. That was the concept of the expansion of numbers that you can see here. And this is the general form that I have talked about that. Now, for example, if we have a number in the base 5, you can see here, if I have a number in the base 5 in this form, we cannot read this number as 4021.2. This is wrong because this number is not written in the actually decimal number. This is written in the base of the 5. So we can read it 4021.2. Similarly, I can say that 4 multiplying by 5 to the power of 3 plus 0, this 0, multiplying by 5 to the power of 2 plus 2 multiplying by 5 to the power of 1, etc. up to the end. And in the case of the octal number system, when the base is 8, same thing happened. 1 multiplying by 8 to the power of 2. Why? Because the value, the place of this 7 is 0, 1, 2, 8 to the power of 2. 2 multiplying by 8 to the power of 1, etc. up to the end. And the fraction part is written by the -1, -2, -3 powers of the 8. If you calculate this value, you can find the corresponding number of this number in the decimal system. It means that 1 to 7.4 in the base of 8 or in the octal system is equal to 87.5 in the decimal system. And this is so important that you have to note that the digit 8 and 9 cannot appear in the octal number, because we said that always the digits, accepted digits in the R base systems are equal to R minus 1. Okay, so again, in the hexadecimal system, I have explained that what's happening. We said that instead of 10, 11 up to the 15, we use A, B, C up to the F. And similarly, if I want to show you that how we can expand this number which is written in the hex system, we can say that B is 11 because the B multiplying by 16 to the power of 3 up to the end that you can see here. The most important reason that we want to actually use the hexadecimal and octal systems in the binary system is that we know that the 16 and 8 are the power of 2. It means that they are kind of the binary system. And when we use the hexadecimal and octal systems in the digital system, we can compact the information. So like this one, you can see that this information which is written in the binary system has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bits. Now we can represent these 16 bits of the binary numbers as a 4-digit in the hexadecimal system. So this is so important concept that we want to use the hexadecimal numbers. And the powers of 2 also so important because sometimes we need to convert these one to each other, and when we want to find and convert especially when we want to convert the binary to the decimal, we will use from this power of the system. Are familiar for you, so actually I recommend you that learn these powers of 2. Now